here's the list of all the functions on this one virus genome we're looking at. And the ones that are highlighted in this color, those are the ones for which nobody's figured out what the function is. Right? Completely unknown. It's been studied for 60 years. About 40% of the parts, right? 40% of the functions, we don't know what they do. So it'd be like lifting up the hood of your car or taking apart your computer and you're like, what the heck's that? 4 out of 10 times. But with the computer or the car, you get to go talk to the engineer, maybe, right? In this case, you don't have anybody to go talk to. If you go down and look at one lower level, and this will be as detailed as I get, this is the specific genetic sequence on part of the virus's DNA. So the letters here are the DNA sequence. This number, that refers to one function, one biochemical function, number 2.8. And then number 3 is a separate biochemical function. So it's like having an if statement and an else if. And somehow the machine language that they're using to encode the functions actually overlap in the same piece of genetic material. So this sequence comes in and stops at this TAA, and then this next one, this 3, starts up at this ATG. I have no idea what this does. If it's important, if it's some sort of data compression, right, so that the DNA doesn't have to be as long as it might be otherwise, or if there's some sort of coupling, as this DNA is read out, it controls whether or not this DNA is read out. It also means that if I have an idea like, I want to get rid of 3 or I want to make more 3, I can't do that without at least mucking up 2.8. I don't have independence of manipulation. So if I'm trying to reverse engineer natural biological systems, I've got situations where for basically everything we're studying, about 40 to 50% of the components, nobody has a clue what they do. And then if you look at the source code or the machine language, it has